Hi, this is Rashid, and I'll be talking about Aerogel today. You might ask, what is Aerogel? Well, this is it, the world's lightest solid material known to mankind. They're just slightly heavier than air because they're composed of up to 99.98% air by volume. In fact, some of the lightest aerogels, if vacuumed from air, can be lighter and less denser than air itself. Now you might ask, why was aerogel invented? How is it made? Why is it such a good thermal insulator? And what is it used for? Well, aerogel was first created by Samuel Stephens Kessler in 1931 as a result of a bet with Charles Leonard over who could replace the liquid in jellies with gas without causing shrinkage. Kessler's later work included alumina, chromium, and tin dioxide-based aerogels. Keep in mind, aerogel is not a single material with a fixed chemical formula. Rather, the term is used to group all materials with a similar geometric structure that makes them aerogels. Now, let us take silica aerogel as an example to understand the structure of aerogels. Silica aerogels are typically synthesized by using a sol-gel process. The first step is the creation of a colloidal suspension of solid particles, known as a sol. The precursors are liquid alcohol, such as ethanol, which is mixed with a silicon alkoxide, such as tetramethoxysilane and tetraethoxysilane. The solution of silica is mixed with a catalyst and allowed to gel during a hydrolysis reaction, which forms particles of silicon dioxide. The oxide suspension begins to undergo condensation reaction, which result in the creation of a metal oxide bridges, either MOM, which is also called OXO bridges, or MOHM, which is also called OL bridges, linking the dispersed colloidal particles. These reactions generally have moderately slow reaction dates, and as a result, either acidic or basic catalysts are used to improve the processing speed. Basic catalysts tend to produce more transparent aerogels and minimize the shrinkage during the drying, and also strengthen it to prevent pore collapse during drying. Then, when silica gel is obtained, liquids inside the structure must be dried out and replaced out by air. This process, supercritical drying, also known as critical point drying, is a process to remove liquid in a precise and controlled way, in the absence of surface tension and capillary stress. Now that you know how supercritical drying works, here is how it applies to aerogels. The first step, a gel is prepared using a sol-gel chemistry. The gel contains a mixture of organic solvent and water in its pores. The second step, the gel is soaked in a pure organic solvent several times over the course of several days to remove the water from its pores. The third and final step, the gel is supercritically dried in a pressure vessel one of two ways. The first one, the gel is placed in a pressure vessel filled about halfway with the same liquid held in its pores. The vessel is then sealed, heated past its critical temperature and pressure, and then is isothermally depressurized to give aerogel. The second way, the gel is placed in a pressure vessel with liquid carbon dioxide. The liquid carbon dioxide is essentially another solvent that can displace the liquid in the pores of the gel. The gel is soaked in liquid carbon dioxide over the course of several days, flushing new carbon dioxide to replace the solvent in the pores of the gel. After the solvent in the pores of the gel has been replaced, the carbon dioxide is heated past its critical temperature and pressure. The vessel is then isothermally depressurized to give aerogel. Now that we generally know how aerogels are made, we can move on to its wondrous properties and uses. As we know, aerogels are extremely porous. Scientists use the term mesoporous to refer to materials that contain pores ranging from 2 to 50 nanometers in diameter. This property is what makes aerogels made up mostly of air, and we all know that air is a great insulator. Let's take a look at this video. Here in a controlled environment, a piece of aerogel is placed over a Bunsen burner. The hottest part of the burner, reaching temperatures of 1500 degrees, is the tip of the flame, which is touching the aerogel. However, the scientist has enough confidence in its insulating properties that he just casually places his hand over the aerogel. Here is how insulation works in aerogel. If we zoom in on the nanostructure of aerogel, you will see it has a sponge-like structure with tiny pores, just tenths of nanometers apart. It is a better insulator than air because those pores are so tiny that hot air struggles to diffuse through them. Plus, the nanostructure itself is a poor conductor of heat. This is called the Knudsen effect. Another property that is related to porosity is surface area. A single small-sized cube of aerogel has a surface area of half of a football field. That enables aerogels to be highly absorbent of water and other fluids. Another characteristic that helps with the absorbency of water is that its structure is covered with hydroxyl groups, which specifically attract water. That is why many museums use aerogels to preserve priceless paintings from humidity. But this property can be reversed. Yes, the very water-absorbent aerogel can be made waterproof. After the process of creating aerogel, it will contain a large amount of hydroxyl groups on the surface. The hydroxyl groups can cause a strong reaction when the aerogel is placed in water, causing it to catastrophically dissolve in the water. One way to waterproof hydrophilic aerogel is by soaking the aerogel with some hydrophobic chemical base. This chemical reaction rearranges with the OH groups, creating a huge nonpolar group, which is water repellent. As you can see in this video, this paper was treated with aerogel, making it water repellent. Now that we all know all about aerogel's properties, let's take a look at its applications in everyday life. The remarkable characteristics of silica aerogel, low density, lightweight, and unmatched insulating capability, attracted NASA for cryogenic insulation for space shuttle and space exploration mission applications. For example, when a shuttle is fueled, it requires more than 500,000 gallons of cryogenic liquid oxygen and liquid hydrogen. To remain a liquid, hydrogen must stay at cold -253 degrees, and liquid oxygen must remain at a -183 degrees. The systems necessary to deliver, store, and transfer these cryogenic liquids call for long, high-performance insulation technology at all steps along the way and into space. In 1992, NASA started to pursue the development of a practical form of aerogel. Up until that point, aerogel had always been too fragile to handle in its monolithic or solid form, and too time-consuming and expensive to manufacture. The concept for a flexible aerogel material was introduced by James Fesmire, the senior principal investigator of the Cryogenics Test Laboratory at Kennedy Space Center. Fesmire, at that time a mechanical engineer responsible for cryogenic fueling systems design, envisioned an aerogel composite material that would be practical to use, but would still exploit the phenomenal heat flow stopping capability provided by the nanoporous aerogel. Some places on Earth face harsh weather conditions over prolonged periods of time. North Canada, the North Pole, Antarctica, and many other locations on Earth have extremely low temperatures that go as low as -80 degrees. Such deadly freezingly low temperatures can make expeditions for scientists or even normal day life for locals extremely hard to cope with. So a company called Suppilt Incorporation launched a Kickstarter campaign introducing Kessler Aerogel Jacket, the warmest and thinnest jacket on Earth, promising to keep people warm in temperatures as low as -196 degrees. Aerogel is a mesmerizing material. Its diverse and versatile properties have attracted scientists and even industries to develop it to the market needs. Nowadays, you can find aerogel in your jackets warming you up, in your swimsuits making you waterproof, or in the ceiling above your head insulating your house from the cold winters and hot summers. And that's all you need to know about aerogel.